In this video, we are going to solve the polynomial inequality, and I'm going to go ahead and demonstrate how to solve it with two different methods. So the first method is graphically, and the second is algebraically, using something that is called the interval test method, or a sign analysis. So please, if you know you prefer method 2, go ahead and fast forward the video. So anytime we have a polynomial inequality, we always need to begin by expressing the function compared to 0. And in this particular case, you'll notice that it's already greater than or equal to 0. So that step essentially has already been done for us. So now we're going to take a look at the left-hand side, the expression, and we're essentially going to treat this as a function and think about what the graph of this function would look like. So y equals x plus 2 times x squared minus 2x plus 1. We're thinking graphically, trying to figure out what this function would look like. So it's helpful to find the x-intercepts when we're graphing. So these would be the zeros. So if we set y equal to 0, basically setting this function equal to 0, we can find those x-intercepts. And what's particularly nice about this function is it is already in factored form because it's written as a multiplication problem. However, there's a chance that this second factor, x squared minus 2x plus 1, it may factor further. So let's go ahead and try to factor that second factor, x squared minus 2x plus 1. It's a trinomial, so we'll try to factor it into two binomials. And it looks like x times x will give us x squared. And if we have negative 1 times negative 1, let's go ahead and check that factoring. We'd have x times x is x squared. That would be negative x. Then we'd have another negative x, which will be negative 2x. And then negative 1 times negative 1 indeed is positive 1. So this does factor further. It factors into x minus 1 times x minus 1. So we really get 3 zeros, negative 2, and positive 1, but you'll notice positive 1 appears twice. So this is what we call a multiplicity. And if you remember back to when we graphed polynomial functions, when we had an even multiplicity, we called that a bounce, which meant that the graph is going to bounce off of the x-axis at the 0 that had the even multiplicity. Sometimes we also called it a touch. It touches the x-axis, in this case, at x equals 1. So that's going to be really useful now as we build the graph. So I'll go ahead and plot my x-intercepts, negative 2 and positive 1. And then I also need to think about the shape of the graph. So looking at the function, y equals x plus 2 times the quantity x squared minus 2x plus 1. Now that's in factored form, but if I had distributed, x times x squared would be x cubed. So I ultimately have a function here that is degree 3. So this is a cubic, and we know cubics are going to have an S shape. Now looking at the leading coefficient here out front, which is a positive 1, that tells me then I know that this is an S that is going to rise. It's going to rise to the right. So let me show you that end behavior. The right-hand side of the graph is rising. The left side of the graph is falling. And therefore, I can put that end behavior together with the x-intercepts, and I can create a decent graph. So I know this graph is going to cross through the x-axis at negative 2, then it's going to bounce off the x-axis at positive 1, and eventually rise to the right. And again, it falls to the left. So now we are going to use our graph to solve the original inequality. So the original inequality is set greater than 0. So greater than 0, that means we're looking for y values that are greater than 0, which means we are ultimately interested in the portion of the graph that lies above the x-axis. So if you have a highlighter, grab your highlighter and highlight the portions of the graph that lie above the x-axis. In this case, it would be this entire portion of the graph that lies above the x-axis. Now, we also need to consider the x-intercepts. We need to consider the -2 and the +1. Well, notice in the original inequality up here asks us to find where this expression was greater than 0, not greater than or equal to. So therefore, we are not going to include -2 and +1 because at -2 and at +1, remember the output, the y values there, are equal to 0. And we don't want to be greater than or equal to 0, we just want to be greater than 0. So this means we are not going to include those x-intercepts in our solution. So our solution will be all of the x values from -2 to +1, and I'll use a parenthesis on both of those so that I'm not including those in my solution set, and then all of the x values from +1 to infinity. So this is the interval notation way of writing our answers, our solution. Now let me demonstrate the algebraic method, which is often called a sign analysis or the interval test method. And you begin very much the same way. You still need to write the expression as a function compared to 0, and that's already done for us. And then we basically need to find where the function is equal to 0. So setting this function equal to 0, we're finding the zeros. That's basically the same thing we did before. We go ahead and continue factoring. And if that trinomial there, x squared minus 2x plus 1, let me mention, if that did not factor, then you would need to do the quadratic formula. In this case, though, it factors. So we have that x minus 1 times x minus 1. And therefore, my zeros are x equals -2 and +1. And if you want to write that +1 appears twice, you can. Now, the difference between solving this graphically versus algebraically is now we're going to take these zeros, which we call the boundary points. Some people refer to these numbers as boundary points. And we're essentially going to be putting them on the number line. And we'll put them in order from smallest to biggest. So we have -2 and +1. And that basically divides our number line into 3 intervals. So now we're going to pick some test values. And we're going to test a number. We want to test a number that is in this interval, which would be smaller than -2. So perhaps you would test -3, for example. But any number smaller than -2 works. Then we test a number that is between -2 and 1. 0 works well here. And then we need to test a number bigger than 1. So 2 will work there. So we have 3 test values. Now the idea with the interval test method is you're going to test these values into the factored form of our expression. So that would be here, x plus 2 times x minus 1 times x minus 1. And we want to keep track of whether the outputs are positive or negative. So, for example, if we take -3 and substitute it in for x, -3 plus 2 is a negative number. Now, it's -1, but I'm not actually going to even write the value. I'm just going to keep track of the sign. That's often why we call this a sign analysis. Plugging in -3 here, -3 minus 1 is also a negative value, and -3 minus 1 here is another negative value. So a negative times a negative is a positive, times another negative results in an overall negative value. And then I like to put a little negative, I like to put it under the number line here because I can't help but think graphically that when I get a negative output, that graphically that means a negative y value. So my graph is below the x-axis. You can, of course, put the negative above the number line if you want to. But that just means that any number that I choose that is smaller than -2, it's going to yield an overall negative output. So then I move on and I test x equals 0. So 0 plus 2 is a positive, 0 minus 1 is a negative, and 0 minus 1 is another negative. So this is an overall positive result, so I get a positive output in that interval. And then I test positive 2 the same way. Positive 2 plus 2 is positive. Positive 2 minus 1 is positive. And 2 minus 1 is another positive. So that's a positive output. So any value that is greater than 1 will give us a positive output. Now let me mention, if you noticed something here algebraically, let me just scoot this over at this step. If you noticed that we really had x minus 1 times x minus 1, which could be rewritten as x minus 1 squared, then good for you, because that would have actually saved us some time. In other words, this portion here, x minus 1, the quantity squared, no matter what value I plug in for x, because I'm squaring this quantity will always result in a positive, no matter what. So really, you don't even have to consider that factor because it's always positive. You only need to consider the sign of the x plus 2 quantity. And if you notice that, and that saved you some time on your testing, then good for you. That's a great way to use your algebraic knowledge to be a little bit more efficient. Now that I've done the sign analysis and I've done my testing, then I'm going to go all the way back to where I had the inequality compared to 0. In this case, it was greater than 0, which means that I am ultimately looking for positive outputs. If I am greater than 0, that means my number is positive. So looking at my number line, I am going to be choosing the intervals that gave us positives. So I'm going to be highlighting basically the positive intervals. And right now that looks like everything greater than negative 2. But once again, I do have to consider whether or not it's greater than or equal to. And again, this inequality here, it just says greater than 0, not equal to 0. So that means we are not going to include those zeros. So we would be using parentheses then, so that we are not including x equals negative 2 or x equals 1. So writing that final answer in interval notation, our solutions will be all of the x values that are an element of the intervals in this case, negative 2 to positive 1, a parenthesis so it's non-inclusive, and then positive 1 to infinity. So you get the same answer, just another approach, an algebraic approach rather than a graphical approach.